Friday is so much better than Wednesday. I love Friday. Let's get this today really quick. All right, so we have office hours today. What time? 12:30 to 1:30. We have workshops Sunday 1 to 3. Office hours Monday and Tuesday both. And then the exam is next Wednesday. So there's going to be a lot of opportunity to come see me if you have some questions about stuff. All right, so I realized I hadn't really updated you on stage recently, and so I snapped a picture as I was walking out the door this morning. She always looks that sad. She just sits on the rug and looks like she's abused or something. But we love her and she's not. Shouldn't even joke about that. All right, so I was talking to my wife this morning, and I was like, man, I love doing all the demos and things that we got to do at 103. It is so much harder to get these things lined up when you have 300 plus students versus like 115 last semester. So I was kind of taking a trip down memory lane. And so who of you were in my class where I got to have Reevely come in and do the app? So I got some pictures and stuff from that. So there's Reevely trying to blow up a balloon. You'll see that he actually struggled a little bit with it. And so here, I was clearly just like not even caring about my appearance at that point. I mean, I hadn't had a haircut since I got married, which was the end of July. And then this picture was like November. So anyway, I don't think I touched my beard either. So I look bad. Look at me standing next to him in a suit. All right. So let's see. Here he is trying to blow up a balloon. I thought we'd just have a little fun for a few minutes. We've been working hard. It does take some skill, I guess, to blow these things up quickly. All right, so this then, I of course was eating my oatmeal this morning, and as I always do. And I was browsing The Economist like a 60-year-old man does, and I came across a little section in the science part, which of course I'd be reading. I read it all, but I happened to be reading the science part, and they talked about the Brussels attack a few weeks ago. Specifically, they were talking about new chemicals that the bad people are basically using to be more deceptive and things. And so I thought we could talk about that for a few minutes because I thought that it was an interesting piece of chemistry, even if it's ultimately related to what are terribly heinous acts. All right, who remembers this demo from last semester? All right, so this, I think I blinded a few people for like 10 minutes during class. So what it is we have what seemingly looks like a balloon. So the balloon has hydrogen in it, but that's not the exciting thing here. What we have is what seemingly looks like cotton. And so this is actually not regular cotton, this is gun cotton. So let's talk about what gun cotton is. And so that will ultimately lead us to a discussion about these new things that people are using. So let's see. Regular cotton is basically a polymer, and you don't have to write this down. This is for fun. So regular cotton looks like it's a polymer of carbohydrates, and so it's made up of stuff that looks like this. Now, what I did in making that new cotton, what I'm calling gun cotton, is I soaked it in HNO3, and so that of course is nitric. So I soaked this thing in nitric acid for like a day, and then had to just rinse the hell out of it because it's scary. I mean, it's just soaked with nitric acid, which is bad stuff. It was actually a combo of nitric acid and sulfuric, real nasty brew. And so ultimately, what this made was nitrocellulose, where the OH groups have been replaced with NO2 groups, and so that's what made gun cotton so different. And so when we think about what would happen if we set, say, a cotton T-shirt on fire, would a cotton T-shirt be flammable? Sure, right? I mean, I could certainly set my shirt on fire, but would it be, I mean, really, really dangerously flammable to the point of almost exploding? No, because it's a cotton T-shirt. But what I essentially did was I changed the structure of the cotton to gun cotton. So gun cotton, again, is nicknamed for nitrocellulose, and so this does not react like typical cotton. So this is the point where last semester I was like, don't look at it directly, because I actually did and couldn't see for a few minutes. So this is what happens when you light gun cotton on fire. That is not like typical cotton. Typical cotton would burn slowly. It would be very sooty. And honestly, the neat thing about gun cotton is, so regular cotton would probably set off the fire alarm, but gun cotton actually burns really cleanly because it doesn't create soot and smoky stuff. So we'll just watch it again. Yeah. I don't know if did Meldrum do the balloon in his class along with it? Yeah, because that was my idea. I just didn't want to take credit for it. Okay. So anyway, what this leads us to is the thought about how organic molecules can basically be made into dangerous molecules. And so one common molecule that's used as a solvent in organic chemistry. All right, so you know what this is, right? This is benzene. And so what about this? It's not phenol. If it was an alcohol, it'd be phenol. So this is methylbenzene that goes by the name of toluene. And so toluene can also be made into a relatively dangerous molecule. And so toluene, what we can do is I'm not sure how to probably soak it in nitric acid. We can react it such that essentially we add those same dangerous NO2 groups that I was talking about. And so what's the name of this molecule? All right, it's got 3 nitro groups, so what do we probably call that? Trinitro, and then it's just toluene, right? So we've got trinitro toluene, or for short, TNT, right? So that's TNT. It's just an organic molecule like toluene. We've added some nitro groups, and then boom, we have TNT, which is basically the standard for which all explosives are compared to. This is about as basic as it gets in terms of an explosive. And so the way that trinitrotoluene is made so dangerous is because on reaction, if we take about 2 moles of our trinitrotoluene, it ends up making about 15 moles of gas. And so how much room does 1 mole of gas take up? At atmospheric pressure, I should say. 22.4 liters, right? Everyone remembers that. And so 15 times 22.4 is a lot of volume. And so if we're immediately just making all this gas, that obviously is going to displace other gases along with buildings, right? It's going to push a lot of stuff out of the way. And so it's a really dangerous explosive. Fortunately, we've gotten to a point now where we don't have to worry too much about people sneaking, say, TNT onto a plane. So the reason is we figured out ways that we can detect these explosives. And so the way that we detect these explosives is basically we're able to detect the nitrogen in them. And so one thing that the vast majority of explosives have in common is that they contain nitrogen, because nitrogen, when it reacts, makes lots of gas, right? And so we'll often find nitro groups on explosives. So this isn't really used clandestinely anymore, and other nitrogen-containing explosives aren't, because they're easily detectable. And honestly, I've often worried going through security at the airport if they're going to be like, "Sir, we detect nitrogen on you," because I worked with stuff, and I'm going to be like, "Oh yeah, I was around it earlier." I was actually around some precursors earlier. So, but that's never happened, and I don't work with chemicals. So I'm okay. I've never had to deal with it, but I have worried about it. Okay, so back to The Economist. So this article was about the explosive that was used in the Belgium attack, and so what that is, that chemical. I'm doing this all from memory. So it was TATP was the name of this molecule, and so what this stands for is triacetone triperoxide. Okay, so we know what acetone is. Acetone, everyone is familiar with acetone. If you haven't used it in lab this semester, you've maybe used it to like get the nail polish off of your nail, right? So, or the whatever girls do with nails, that stuff. And so so basically we're going to take another seemingly innocent organic molecule and it can be made dangerous by reacting it with H2O2, which is just hydrogen peroxide, right? So I think I've spoken a few times, at least this semester, on the dangers of peroxides, and so specifically in lab. we don't let our distillation go dry, right? Because we could have a small amount of peroxides in our solvent, which can be dangerous because that explodes. And so the dangerous thing about peroxides is that we ultimately have oxygen-oxygen bonds, and those just are not very stable. They do not play along very well when they are contained in organic molecules. So what happens, and what's being done now to basically get by our safety measures of detecting most explosives, is people are coming up with things like triacetone triperoxide. And so what this molecule looks like, it ends up, so we end up with a trimer. It looks kind of like this, and so we can see where the acetone part is. It's the this part, and then what we've got is connected by peroxides. And so this is a particularly dangerous molecule, number one. So I think it is a 9-membered ring. And so interestingly enough, we haven't talked a lot about ring strain as we get into larger rings. So we saw that as we go from 3 to 4 to 5 to 6-membered rings, what happens? Do we decrease or increase ring strain? We decrease, right? And so 6-membered rings don't have really much strain at all. That's what makes them so stable. But interestingly enough, once we start going past 6, we start increasing the ring strain again. And so once we get up to around the 9, 10, 11-membered ring number, that's actually a really highly strained ring. So here we actually have lots of ring strain due to this being a 9-membered ring. And then furthermore, what we've got are oxygen-oxygen bonds. And so this is what, basically what's going on behind the scenes by the bad guys to get past the measures that we have to detect explosives. And so it's a continuing battle. And there's no joke that goes along with it. This stuff pisses me off more than anything. But this is kind of the science. So there's still some interesting science that can go on behind the scenes when this stuff's going on. So. Anyway, I guess we don't end on a great note, but it's still it's interesting. Okay, so let's get back into Orgo 2. I think we're going to be perfectly fine on exam 3 preparation. So we'll cover part of that today and then finish it up on Monday, and we'll go from there. We'll be ready for the exam. Okay, so let's remind ourselves what we were doing last time. Or really, let's remind me. So we were looking at the electrophile structure, and so we were talking about our section where we need more info, right? So we don't have enough information to figure out if we're going to go SN2, SN1, and so that's going to be a big part of what nucleophilic substitution, what this chapter covers, and so that's going to be a pretty big part of the exam. Okay, so we talked about, first off, we want to look at structure, and we looked at some electrophiles that can undergo both SN2, SN1, so we said secondary electrophiles can't. But also some primary electrophiles, such as allylic halides or benzylic halides, and so that's because we have a resonance stabilized cation that allows those to compete. So today, let's just kind of summarize where we're at. So let's say, if we have something, a molecule that looks like this, and so we have some generic leaving group, plus a nucleophile, we're going to have 2 possibilities in terms of mechanism. And so if we go SN2, how many products can we form? Just 1 product. And so that's going to be the inversion product. So if we go SN2, we're just going to end up with our inversion product. But we could also be going SN1. And so in SN1's case, how many products can we form? I've just drawn 2, so 2. All right, so in this case, we can still get our inversion product, but we can also get our retention product. And so the easiest way to, when we're drawing the inversion of the retention product, if it's the inversion, we're just going to change our leaving group from a wedge to our nucleophile on a dash. And then vice versa, if we're talking about the retention product, we're going to keep the stereochemistry and just swap out the leaving group for the nucleophile. All right, so what we're going to have to do as we go forward is we have to decide. We have to decide. And so in a lot of cases, it's an easy decision, but in others, we have to put a little more thought into it. Now, here's the key. There's a couple of ways to think about this. We're going to learn about different variables and how it can favor SN2 or SN1. And so in a lot of cases, you can get bogged down thinking, gosh, this favors SN2, while this other thing favors SN1, and then one of the variables actually it doesn't favor either. And so we're going to make this as simple as possible. The way that we can make it as simple as possible is we're going to say, if it's possible to do SN2, we are absolutely going to do it. If we can do SN2 is almost always the goal synthetically because we only get one product, we get really good stereo control. SN1 kind of sucks because we have carbocation rearrangements, we have multiple stereo products that can form. If we can do SN2, do it. So we're going to look for, basically, we're always going to be keeping our eye out for reasons that we can't do SN2. That's the only thing that we really care about. All right, so for example, thus far, what we've seen in class is we could say, have this electrophile. And so what kind of electrophile is it in terms of its substitution? How many carbons are connected to the middle carbon? Yeah, so this is a tertiary electrophile. And so we're going to react it with iodine, which we've seen react in an SN2 fashion thus far. And so what we're going to have to ask ourselves is, well, is this going to go SN2 or SN1? And so we look at our electrophile. We see that it's tertiary. Now we always want to do SN2 if possible. With this electrophile, is it going to be possible to do SN2? No, and it's because of the crowdedness, right? So when we talk about SN2, we've learned that a tertiary electrophile just won't undergo that pathway because it's too crowded. And so now we've got a case. Can we do SN2? No, we're done. We have to go what mechanism? SN1, and so that's what we do. And in a lot of cases, we might expect two products, but because we don't have a chiral center here, we'll just have the one product. It's not bromine, iodine. All right, so we have to go SN1 because we just can't do SN2. And so that's really what we want to be on the lookout for is can we or can't we do SN2? All right, so the one situation we've learned thus far is when we have a tertiary electrophile, we are unfortunately unable to do SN2. So we'll say no SN2 allowed. That's our only really limiting factor that we've learned. All right, so the next thing up we're going to talk about is going to be part C, and so that is the nucleophile. So we've talked about the structure of the electrophile. Now we're going to talk about the structure of the nucleophile and how that can be limiting or it can allow us to do SN2. So let's think back. Let's remember that for an SN2 reaction, when we discuss the rate, we say that the rate is equal to the rate constant times the concentration of the nucleophile and the concentration of the electrophile. And so from that rate equation, we can say that the concentration of our nucleophile, does it affect the rate? What would happen is, say, initially we started with 1 mole of nucleophile and 1 mole of electrophile. But let's say we double the amount of nucleophile to 2 moles. Would that affect the rate at all? Yeah, the rate would double, right? And that's because the rate is dependent on both the concentration of the nucleophile and the electrophile. So the concentration of the nucleophile absolutely affects the rate of our SN2 reaction. But that's not the only aspect of the nucleophile that affects the rate. So what we find is that so does the nucleophile strength. And so that should make a little bit of sense, right? Because in an SN2 reaction, what's happening is the nucleophile comes in and attacks the electrophile and it just punches the leaving group away, right? It forms a new bond while the leaving group is pretty much left out on its own. And so the nucleophile strength, we'll say that the nucleophile must be strong enough, and we'll use punch, to punch away the leaving group. If it's not strong enough to punch away the leaving group, do you think we're going to be able to do an SN2 reaction? No, it's just not going to happen. We need that reactivity from the nucleophile. We need it to be highly attracted to our electrophile so that it will react with, I guess, enough force to, again, punch away the electrophile, or the leaving group. Okay, so let's, before we talk about some details, let's just go ahead and have down on paper. We have two cases. We can have the case of the strong nucleophile, or we can have the case of the weak nucleophile. And so is a strong nucleophile going to favor SN1 or SN2? Definitely SN2, right? And so that means if we have a weak electrophile, well, what's that going to favor? SN1. And so in the case of a weak electrophile, what happens is we don't have that strong attraction between the nucleophile and the electrophile. And so pretty much the nucleophile just waits until the electrophile becomes a carbocation, and then it will come in. But it needs that extra boost to actually be attracted to the electrophile. All right, so what affects nucleophile strength? We're going to spend a little bit of time here. So what affects nucleophile strength? All right, so the first thing we'll talk about is going to be basicity. So basicity and nucleophilicity have a little bit of a trend, but they're not the same thing. We'll talk about why that is. So what we can say is that in general, and we have to say in general because this is not the truth in all cases, but it is very true in most cases. So in general, stronger bases make stronger nucleophiles. And that should make a little bit of sense based on what we've learned thus far. So let's see if we can compare some things that would bring this together. So let's say that things that like to do this, the least sciencey thing I've ever written. Yeah. Things that like to do this. Things that like to do this. And so in this case, we're going to use hydroxide. So we're going to react it with HA. And so we know that hydroxide is a strong base, and so in this case, we're going to react it as a base. And so if we draw an arrow-pushing mechanism, we'll start at a lone pair, and we'll draw over, and we'll grab our proton, right? And so then we're going to have our A go away. Would you say that the A looks a little bit like a leaving group in this case? It definitely does, and so we'll compare the two possibilities explicitly here in a sec. All right, so we end up with A minus there. So things that like to do this, then we'll say also like to do this. Very specific phrasing. All right, so again, we're going to use hydroxide. But in this case, what we're going to do is we're going to replace our proton with a methyl, and then we're going to replace our A with a leaving group. And so again, the reaction we would expect to take place, we have a methyl halide here. We could do SN2. And so again, we're going to start our arrow at our hydroxide, draw it to our methyl, and basically, undergo an SN2 reaction. So in that case, we end up with, again, another new bond between our oxygen and something, in this case, a methyl group. And then we have our leaving group that's gone its own way. All right, so in this case, we have our hydroxide acting as a nucleophile. And so now that we have these two pictures down on paper, would you say that an acid-base reaction and an SN2 reaction are pretty similar? I would definitely say so. And so that's why we see that general trend. Something that likes to do this reaction generally likes to do this reaction at all. But they're not the same exact thing. So let's think about why that is. When we talk about acid and base strings, we use pKa. We use pKa's, and we're talking about equilibria. And so when we talk about equilibria, is that a thermodynamic sort of concept? Yeah, it very much is a thermodynamic, right? And so it can be either thermodynamic or kinetic. And so it's definitely going to be a thermodynamic sort of concept. So really, when we talk, I guess, about acid-base reactions, remember, we don't use a single arrow. We actually use our equilibrium arrows here. And so that's because we can tell acid strength basically by letting these things react and then measuring how much stuff we have over here versus how much stuff we have over there. So it's a thermodynamic concept. But when we talk about a nucleophilic substitution reaction, and specifically an SN2, now we're thinking about the rate at which this goes on. And so what we're thinking about, the way that we measure nucleophilicity is we ask ourselves, how fast will this reaction go on? The faster it goes, the stronger the nucleophile. Is rate a thermodynamic property? It's not. What kind of property is it? Yeah, if it's not thermodynamic, then it is kinetic. And so while they have very similar characteristics, we're ultimately talking about two different things. In an SN2 reaction, we're talking about the rate. In an acid-base reaction, we're talking about the equilibrium, and so we don't see that this trend always works, but in general it does, and it does because mechanistically you can see they work very similarly. All right, so another thing we can say is that in general, and again, this isn't perfect because the relationship between bases and nucleophiles isn't perfect, but we can say that in general, strong nucleophiles are going to be bases with conjugate acids of pKa greater than 11. And so any conjugate acid that has a pKa of greater than 11 is going to be a pretty weak acid. And so that's what we want to do if we need to determine whether we've got a good nucleophile or not. So we can think about its conjugate acid, and in general, if it is higher than a pKa of 11, we're going to have that strong nucleophile that will be necessary to do an SN2 reaction. All right, let's look at an example. Let's compare a couple of nucleophiles. So we'll show this electrophile, and so we're going to have two cases. So in one case, we're going to use methoxide as our nucleophile. And then what we're going to do is we're going to compare that with the reaction of this deprotonated ammonium. So we've got an O- versus an N-, and we want to ask ourselves which SN2 reaction is faster. And so we've seen that it can be dependent on the concentration of the nucleophile. We're going to assume that the concentrations are the same, and so then we have to think about the strength of the nucleophiles. And so what we've learned is that the strength of a nucleophile often parallels its basicity strength. Okay, so first off, what kind of electrophile do we have? Will this allow us to do an SN2 reaction? It's a primary. Can we do an SN2 at a primary? Yeah, absolutely. So there's no reason that we can't do an SN2 reaction in this case. All right, so then we think about our nucleophiles. And so what we want to do is we want to take a look at their conjugate acid. So what's the conjugate acid of methoxide? That should just be methanol, right? And so the conjugate acid of methoxide is going to be basically where we protonate our methoxide, and so that's going to give us methanol. What will the protonated form of, what's the protonated conjugate of NH2 minus? NH3, that's ammonia. And so what we want to do is we want to compare the acidities of these conjugate acids. So when we look at methoxide, what we find is a pKa of around 16 or so. And so seeing that the pKa of its conjugate acid is 16 and is greater than 11, would we expect methoxide to be a strong nucleophile? Yeah, definitely. That is the case. All right, so let's then compare it down here. So the pKa of ammonia is around 36. Is that going to qualify NH2 minus to be a strong nucleophile? Yeah, very much so. In fact, it's about 20 orders of magnitude less acidic than the methanol. Yeah. What's that?
Methanol at base.
You're talking about this methanol? So when we talk about the conjugates, so if we're thinking about the two nucleophiles as bases, we want to think about their conjugate acids. And so the conjugate acid of methoxide is going to be methanol. The conjugate acid of NH2 is going to be just the protonated form of that, which would be ammonia. Okay. So between these two nucleophiles, methoxide and NH2 minus, what we've seen, and using the data we've seen down here, what's going to be the stronger nucleophile? It should be NH2 minus, right? And it's because it is a much, much stronger base than methoxide, and so that's exactly what we see. So which reaction is going to take place more quickly, the top one or the bottom one? Definitely the bottom one. And so again, that is because we'll say that it's faster since NH2 minus is a stronger base. And again, we know that it's a stronger base because when we think about their conjugates, it has a weaker acid. So weaker acid, stronger base. Okay, so that is the relationship with basicity. A few other things matter. So we'll find that size matters. And so what we can say is that bigger atoms are more polarizable. Okay, so we can compare a couple of cases. We can compare, say, bromine, and we can compare iodine. So they can both be good nucleophiles, but basically the bigger they are, the more London dispersion forces there will be, right? Because if we have a small atom, well, certainly there can be some London forces, but a big atom has lots of volume, so there can be lots of polarability, or polarization is that actually the word that can take place. So between bromine and iodine, which is bigger? Iodine. So which is going to be the stronger nucleophile? Iodine. It's just more polarizable, which means that at any given moment, it's more likely to have a little bit of charge buildup in it. And so we find that going down the periodic table, actually, we tend to see more nucleophilic substances, or atoms. All right, so importantly, I want to point out that we're talking about bigger atoms, because we can also come up with a trend for bigger molecules. And so in this case, let's compare. So we've seen methoxide, which looks like this. Let's also compare that to, and so this compound on the right is referred to as tert butoxide. And so we're going to use that a lot more once we get to elimination, but for right now I just want to introduce it. Which do you think is going to be the better nucleophile? Is it going to be methoxide or tert butoxide? Why tert butoxide? Yeah, but let's think about the effect of a bigger nucleophile in an SN2 reaction. So what is it that ultimately determines the rate of an SN2 reaction? Is it carbocation stability? Do we form a carbocation in SN2? No, it's crowdedness, right? And so what's going to determine the rate of our SN2 reaction is going to be the crowdedness of our 5-membered transition state that we've drawn. Which is going to be more crowded in that transition state? This nucleophile or this nucleophile? Yeah, definitely one on the right is going to be more crowded. And so because of that, what we say is methoxide is actually going to be the stronger nucleophile, because tert butoxide is just too crowded. And so in fact, what we can say about tert butoxide, and this is going to be important in elimination, is that tert butoxide simply cannot do SN2. Just too big, it's too high energy. For the similar reason as we don't ever see an SN2 go with a tertiary electrophile. All right, so the same idea. Tert butoxide, though, will be important in elimination as we go forward. Okay. And so that's actually a really good case of where nucleophilicity and basicity are not the same. So what we could have is a negatively charged oxygen versus a negatively charged sulfur. Now, which is more basic? So it's the oxygen. We typically make an electronegativity case for that, right? So it's going to be more basic. It's going to be more attracted to an acid because it has more electronegativity. But in fact, what we're going to find down the road is that sulfur is actually more nucleophilic. So that's one of the obvious cases where basicity and nucleophilicity do not follow the same trend. Up the periodic table, we become more basic. Down the periodic table, we become more nucleophilic. And it's just one of those weird things. It's ultimately because we're talking about a thermodynamic property versus a kinetic property. All right, finally, we'll see that solvent can have an effect on the nucleophile. But we're just going to say C section E on Monday. So we're not going to get to that, but that gets its own section on solvent. That'll probably be the last thing that we talk about as we head into exam 3. Okay, so let's clarify what is strong and what is weak. So let's make a list of strong nucleophiles. And so for strong nucleophiles, we're going to have 3 categories. So basically, halogens. Halogens are strong. We've seen that already. We've seen a halogen do SN2 reactions in class and probably in homework at this point. And in fact, we can say that all of them. A lot of cases we leave fluorine out because it's its own thing, but fluorine's also a pretty good nucleophile, so we count that as strong. Other things that we count as strong nucleophiles include charged stuff. And so specifically, that's going to be a negative charge. So that's going to include hydroxide or some kind of alkoxide, right? So that's a deprotonated alcohol that we're showing there. This also works the same way with sulfur. So an SH minus as well as an SR minus will be a strong nucleophile. And then NH2 along with something like NR2. Those are all going to be really good nucleophiles. And again, it's because we've got negative charges on them, and so those are going to be highly attracted to an electrophile, and so we can definitely do SN2 reactions in that case. Let's also include, let's see, the conjugate base of acetic acid. So if you see something that looks like this, that also will be a strong nucleophile. And that kind of bucks our trend because the pK, what's the pKa of acetic acid? It's like 3 or 4. And so it's not greater than 11, but yet we still see that be a good nucleophile. So that's just, the trend breaks down for acetic acid. All right, other cases will include this anion. And so we see we've got a negative charge on the carbon. And so thinking back to why this would actually be stable at all, does anyone remember kind of where the pKa of that CH bond is? Yeah, so we had this on our first exam. So the pKa is about 25. And so a typical CH bond has what pKa? It's like 50, right? It's pretty much the least acidic proton we see. So in this case, we find that a terminal alkyne, so the proton off of an alkyne, has an acidity that's about 25 orders of magnitude more acidic than the typical CH bond. So this is a great way that we could form new carbon-carbon bonds, which is often a target of different syntheses that people are trying to carry out in lab. Another case is going to be the azide anion, so that's N3 minus. And so what that looks like is basically this very linear structure. Every atom is charged, so ultimately one end of this azide is going to react and give us a nucleophile, or act as a nucleophile. And so furthermore, the very dangerous cyanoanion, so that's the conjugate of hydrogen cyanide. And so again, that's a way that we can have reactivity at a carbon and form a new carbon-carbon bond. What is one, when we look at these bottom cases, what is one general trend that we're seeing? I would say that they are very skinny, right? And so in general, very skinny nucleophiles are going to be pretty good nucleophiles, again, because they're going to form the least crowded 5-member transition state for an SN2 reaction. So that's why these three at the bottom are typically used a lot. Yeah? Yeah. Yeah, they're linear. They're not taking up a lot of space. Like even a methyl group is going to take up a lot more space than these because it has hydrogens coming off of it. But here we've got pretty much a linear carbon, a linear nitrogen. So there's just not, they're very skinny. They're very kind of tube-like, right? So they look like a noodle, an uncooked noodle. Okay. I like that. We're even uncooked noodle. Okay. Are you actually writing that? Who wrote that down? All right, some people wrote it down. And so now we'll come up with a list, or actually, we're going to add one more thing onto our strong nucleophile list. And so in this case, we'll say some neutral stuff. So we don't always have to have a charge to have a good nucleophile. There are cases where atoms make really good nucleophiles. And so what we find is that actually an uncharged sulfur makes a very good nucleophile. So that's where we see, we're going to see one of our trends diverge. So a sulfur, it can be charged, it can be uncharged. It's pretty much always going to be a strong nucleophile. So if you see sulfur, SN2 is definitely going to be a possibility. Another possibility is an uncharged nitrogen. It's kind of like right on the line of where we consider strong versus weak, but we give it strong. It ultimately does react in an SN2. All right, so basically that's it. We can see nitrogen or sulfur uncharged can both be strong nucleophiles. So then we'll talk about our weak nucleophiles. And this list is short, and we're not going to add a lot to it because, again, we're looking for reasons to do SN2, not for reasons to not do SN2. We want to do SN2. So when we talk about weak nucleophiles, basically we're going to say, this is going to be it. We're just going to say neutral oxygen. Neutral oxygen does not act as a strong nucleophile. And there's our example. We're going down the periodic table, nucleophilicity actually increases. So we've seen that neutral sulfur is a good nucleophile, but neutral oxygen, one row above sulfur, is actually weak. And so that's going to include cases such as water or methanol, or really any alcohol, right? We'll just say ROH. That also includes our protonated form of acetic acid. So anytime you see just neutral oxygen, are you going to be able to do SN2? Unfortunately not, because we have to have a good nucleophile to do so. All right, let's look at some examples. So let's say we have this electrophile. What kind of electrophile is it? Yeah, so it's secondary electrophile. Can we do SN2 with a secondary electrophile? Sure. And so we're going to keep pushing that direction. We want to do SN2 if we can. And so our nucleophile is going to be sodium methoxide. All right, so is that going to be a charged or an uncharged oxygen? Does sodium ever make covalent bonds? It does not. So anything over here on this side of the periodic table is ultimately going to be there as a counter ion. These are always going to form ionic bonds. And so sodium is going to be most stable with what charge? Just a plus. So what we have is sodium plus, which means over here, for our O-methyl, what's the charge of that going to be? That's going to be negative. And so that tells us because we have a positive counter ion, we're going to have a negatively charged methoxide. Is a negatively charged oxygen a strong or weak nucleophile? It's strong. Can we do SN2? Yeah, there's no reason we can't. So that's what we'll do. We want to do SN2. And so if we do SN2, how many products will we get? We'll just get one, right? Because we only are going to get the inversion product. And so again, the easy way to draw that is you're just going to invert your wedge to a dash and show your nucleophile on there. All right, so we get one product because in an SN2 reaction, it's a concerted transition state, and we have to undergo our backside attack, and we see that we get our inversion product due to that. All right, so another case. Let's use the same electrophile. And so again, we've got a secondary electrophile, so we can do SN2. Now what we're going to use as our nucleophile, that's not it. There we go. All right, so we're just going to use methanol in this case. All right, so we know we can do SN2 still, so now we want to consider our nucleophile. Is our nucleophile a strong or a weak one? It's weak. Why is it weak? It's neutral, and we know neutral oxygen is not a good nucleophile. So can we do SN2 with this nucleophile? We can't. What are we going to have to do? We've got to do SN1. So basically, we're looking for an excuse not to do SN2. If we can do SN2, do it. Don't even consider SN1. Don't look back. How many products will we get out of this reaction? Yeah, we're going to get 2. So again, we're going to get that same inversion product, but we're also going to get the retention product because we've gone through a carbocation intermediate. And so we have 2 products in this case. All right, another example. Let's use this electrophile. So what kind of electrophile is it? Primary, secondary, tertiary. It's a secondary, right? So at our carbon that's connected to our leaving group, we can see that we've got a secondary carbon. It's connected to 2. And so again, what we're going to react with is, say, this right here. And so is this a good or a bad nucleophile? It's a good nucleophile because we know that we must have sodium plus, which then gives us methoxide, and so that's a strong nucleophile. Can we do SN2? Yeah, we can. If we can, are we going to? Yeah, if we can do it, we do. And so we'll roll with SN2. How many products will we get? Just one. We only see the inversion product. All right, now if we use that same electrophile, yet again, let's change the nucleophile up a little bit. Let's use the solvent of life. H2O. Okay, so again, we have a secondary electrophile. Do we have a good nucleophile? We don't. We have uncharged oxygen. Can we do SN2? We cannot. What are we forced to do? So we're going to do some SN1, and let's think about what all could happen. So first off, what's the first step of this mechanistically? We have to form our carbocation, right? That's the first step of an SN1 reaction. And so when we form our carbocation, what we're going to have is a carbocation that looks like this. And so if we have the reaction of our water with that carbocation, so that means we can have, let's see, this top stereocenter stays the same. We could have a tack from the front, which would ultimately end up as an alcohol after a deprotonation step. And then we'll say we could have this product plus what? Yeah, not an enantiomer, because in both cases, we're not going to do anything to this chiral center. That's always going to be on a wedge. And so we're going to have this product plus the diastereomer, where this hydroxyl group is on a dash. But that's not the only thing that can happen. And so let's consider further, is there any way that we can undergo a shift to make this a more stable cation? Yeah, and so we've got a tertiary carbon nearby. What kind of shift are we going to do? Would a 1,2 methyl shift give us a secondary or a tertiary carbocation? A 1,2 methyl shift would make this into a secondary carbocation, right? But instead of shifting the methyl, what could we do? Let's shift the hydride. And so if we shift the hydride, so we'll do a 1,2 hydride shift, we now will end up with our more stable tertiary carbocation. And so from there, we can have a tack of our water. So let's see, we could end up with this product plus what? It's not meso. It's just not a chiral center, right? Because we've got a plane of symmetry that runs right there. And so essentially, are we connected to 4 different groups in this position? No, it's because the symmetry of the ring means that 2 of these groups are going to be the same. And so how many products ultimately down here will we get? Just 1 product. Okay, so in this case, you do need to keep all the stereochemistry things that we've learned in mind. This isn't a chiral center, and so we won't have formed any other stereoisomer. All right. Finally, let's look at this example. So here's our halide, and then we're going to react this with methanol. All right, so this is a primary alkyl halide, and so can we do SN2 with a primary alkyl halide? Yeah, absolutely. It's going to be really favorable. So then we look at our nucleophile. Is that strong or weak? Yeah, so we have a weak nucleophile, which means can we do SN2? We can't, unfortunately. And so the only possible pathway for this reaction is going to be SN1. But we look back here and we see we've got a primary halide. Does the typical primary halide allow us to do an SN1 reaction? Yeah, we learned that it does not. But is this the typical primary halide? It's not. And so it's not because what we're going to end up with is an allylic halide, or at least what we have is an allylic halide, which is going to form an allylic cation. And so we learned last class that it's certainly going to be possible to form this cation because it is resonance stabilized. And so what that means is that both this carbon and this carbon have cation reactivity. And so just like when we do an allylic halogenation, when we have an allylic cation, we can have reactivity at both carbons. And so we would see multiple products form. We would see this product form from reactivity of our methanol at this primary carbon, but then we would also have reactivity at the secondary carbon. And so in that case, we would see this along with the other enantiomer. So in this case, we have 3 possible products that could form. Okay, we will finish all the material for exam 3 on Monday, office hours 12:30 today. Workshop on Sunday, that's the last workshop before exam 3. When? It's 1 to 3. And so otherwise, have a good weekend.
Are you meeting in 2018?
For office hours?
Yeah.